Part B of this example, again, evaluate the definite integral. This time we have the definite integral from 1 to 5, 1 over x squared dx. Okay, well, let's take a look. We're trying to find the exact area between this function and the x-axis, starting at 1, ending at 5. So we're going to say, okay, we need the antiderivative. Well, I really don't like to think of it as 1 over x squared. Let's think of it as x to the negative 2. I've got the drawing here that's going to be revealed slowly. I'll speak to that at the end. All right, we're rewriting that x to the negative 2. Now I can find an antiderivative. I will add 1, making it negative 1, and then I think, hey, what should be out in front so that the negative 1 can multiply and, become what I have here? Well, just another negative, right? Because the negative 1 would multiply down, make it positive. Then the exponent would drop by 1. So it's negative x to the negative 1, although I prefer to think of it as negative 1 over x. And of course, in these, I draw my vertical line and my 1 and my 5, and I always read that bottom to top from 1 to 5. So I'm going to evaluate this function from 1 to 5. That means I plug in the 5 first, then I subtract, then I plug in the 1. So plugging in the 5, subtract, plug in the 1. Negative 1/5 plus 1 gives me 4/5. And right over here, you can see the graph. That's the graph of my original function, 1 over x squared. I looked at it from 1 to 5, so if I kind of piece off that area, that shaded region, that's got an area of exactly 4/5. That is awesome. Like, that's incredible. I mean, I can find that area so quickly. I find an antiderivative. It takes some thought, but, once you get used to them, these antiderivatives go pretty fast. I plug in a couple numbers, boom, that's it. And I find that area of this curved region, all right, anyway, you can tell that I get really into this because it's so cool. All right, part C, we're going to step up the difficulty level a little bit. Definite integral from 2 to 3. Our function is 32x, quantity x squared minus 4, raised to the 7th dx. Like, oh man, okay. Whew. How are we going to find that antiderivative? Well, there's two options. So I could multiply all this out, right? Multiply that 7 times, distribute 32x. There's a much easier way. You may recall u substitution. What should we pick u to equal here? And if you are sharp on your u subs, you pick what's inside those parentheses. Right? I won't go into the details there. That was back in 5.2. We're going to take u into x squared equal to x squared minus 4. That means du over dx. Well, that's our derivative, right? So that's equal to 2x. And two things happening here. I'm going to multiply the dx over there. But I also realize I don't need that 2, so I'm going to divide it back this way, make it a 1/2. 1/2 du equals x dx. So my substitution can happen. Looking back to my original, that's going to become u, but then my x dx will become 1/2 du. And it's going to leave me with this. Definite integral from 2 to 3. I'm going to leave that 32. It can stay where it is. The rest of it becomes u to the 7th, and the x dx 1/2 du. At this point, I go ahead and multiply 32.5. And even while I do that, I'm going to pull that 16 even in front of the integral sign because it's now just a constant multiple. So I've got the definite integral from 2 to 3, u to the 7th du. Okay. Hey, what is that antiderivative? I'll keep the 16 as a constant multiple. This would be 1/8 u to the 8th, 2 to 3. Remember that before you end a u sub problem, you need to put your what it's equal to back in there. So we need to do that here. Oh, looks like I simplified a little bit. 16 times 1/8. I need to put what u equals back in. So that's 2. Now it's x squared minus 4 to the 8th from 2 to 3. All right. So we go through all the steps of our u sub, get to there from 2 to 3. And now we're going to plug in the 3. That should be to the 8th. We're going to plug in the 2. That should be to the 8th. We're going to subtract in the middle, so plugging in the 3, subtract, plug in the 2. And my final answer is definitely wrong because I forgot that 8th power. Oh, yeah. No one look at that. No one look at that. Lucky for us, this goes to 0. Just a coincidence. Right here, we've got, what, 5 to the 8th times 2? That is 7, 8, 1, 2, 5, 0. There's our final answer. I don't think I'm going to graph this one or give you a sketch of the graph. I don't know what the graph of 32x quantity x squared minus 4 to the 7th is. I guess I could graph it in Desmos. But I definitely don't want to look at that area answer. But we can know, the exact area of this is just from 2 to 3, just one space, All right. I've got one more of these before we move on in the section. I also apologize about this awful shadow coming in. The afternoon sun kind of creeped in during this video. Let's look at the definite integral from -2 to 4 for the function -3x plus 2 dx. So something's going to happen here with the final answer that I want to bring up, and hey, we might as well get some practice with it as well. Let's see. Looking at our function, we need that antiderivative, right? So -3x, that would have come from -3/2 x squared, because that 2 would multiply down, right, and cancel out. Okay. And the plus 2, well, that would have come from plus 2x. Right. Then, of course, we evaluate from -2 to 4. Well, what are we going to do from here? We're going to plug in the 4, then we're going to subtract, and we're going to plug in the -2, like so. Ooh, that shadow's really getting us now. -3/2 times 4 squared plus 2 times 4 minus, big parentheses, -3/2 times -2 squared plus 2 times -2. And I think I looked at each of these one at a time. This one here, grab a calculator, maybe confirm with me that you got -16 right there. Then we subtract, and this whole thing over here, I got -10. So, of course, we end up adding, and our answer is -6. Okay, so we go through this problem, and, nothing unusual. Antiderivatives, hopefully those are fine at this point. We're plugging in numbers. All right, fine. We get this answer at the end, -6, and that's our answer. But that might cause you, some of you out there, to say, wait a second. I thought we were finding area. How is it that we got a negative answer? That's a great question. How can the answer be negative? Isn't this area? It is. We didn't do anything wrong, though. Here's what happened. Okay, so here's a sketch of our function, right, we had f of x negative 3x plus 2, right? So our y-intercept is 2, slope is negative 3. And then I've indicated negative 2 and positive 4. So we looked at the area starting at negative 2, ending at 4. Well, what happened? It's always the area between the function and the x-axis. So at first it's this triangle right there, but then when it crosses over, it becomes this area. Right? It's always the area between the function and the x-axis. What happened here? When the area drops below the x-axis, it gets calculated as negative area when you do a definite integral. This is positive area. This is negative area. And it turned out there was more negative area than positive area. So if you found each of these separately, right, this would like balance out, say, about this much, you know, like that would cancel out with that. But then there'd be some more left over, and that's why we end up with a net negative when it's all done. Okay, hey, let's stop this video right here. More to come. We're going to talk about some properties of integrals next.